Electron domain geometry tells us the shape the electron domains make in a molecule. This will determine the bond angles in the molecule. Remember, though, that electron domains could be single bonds, double bonds, triple bonds, or lone pairs. When it's a lone pair, there is no terminal atom attached. Sometimes we want to sort of ignore the lone pairs and just tell what shape the atoms themselves are making. The lone pair is still important in determining the shape. It just is not part of the descriptive name that we call the molecular geometry. To find the molecular geometry, you could use a combination of number of domains on the central atom and how many of those domains are lone pairs. For example, if a molecule has 4 domains on the central atom and 2 of those domains are lone pairs, the molecule will have a bent molecular geometry. There are electrons pushing out in 4 directions, but the atoms are only going in 2 of those 4 directions. The atoms end up looking like they're making a V or bent shape, sort of like if you took a crowbar and bent it. I like to think of electron domain geometry as the main category and molecular geometry as a subcategory. You have to know electron domain geometry first, and then you need extra information, which is number of lone pairs on the central atom, to determine molecular geometry. We are going to go through the molecular geometries as subcategories based on number of domains. When there are 2 domains, the molecule has a linear electron domain geometry and a corresponding 180-degree bond angle. We'll talk about hybridization in the next chapter, but for future reference, 2 domains will correspond to sp hybridization. If the molecule has 2 domains and 0 of them are lone pairs, that means there are atoms attached to the electrons in both domains. The atoms are doing the same thing the electrons are doing, so it will have the same name. It will have linear electron domain geometry and linear molecular geometry. If the molecule has 2 domains and one of them is a lone pair, that means there are just 2 atoms total in the molecule. 2 points make a straight line, so the descriptive molecular geometry name is also linear for this type of molecule. Anytime that we're left with 2 atoms, the molecular geometry will be linear, so I will leave those types of molecules off the following slides. You will notice that I also have general drawings of each of these molecular geometries. It is a good idea to learn how to draw these so that you can figure out the molecular geometries more easily, since they have descriptive names. If you don't learn how to draw them, you are just going to have to memorize combinations of domains and lone pairs to figure out the molecular geometries. When there are 3 domains, the molecule has a trigonal planar electron domain geometry, a corresponding 120-degree bond angle, and a corresponding sp2 hybridization. If the molecule has 3 domains, 0 of which are lone pairs, the atoms are doing the same thing the electrons are doing, so we use the same name. It will have trigonal planar electron domain geometry and trigonal planar molecular geometry. If the molecule has 3 domains, one of which is a lone pair, the molecular geometry will be bent. Sometimes the bond angle will be included with the name to distinguish it from bent 109.5, which has 4 domains. When there are 4 domains, the molecule has a tetrahedral electron domain geometry, a corresponding 109.5-degree bond angle, and a corresponding sp3 hybridization. 4 domains with no lone pairs is called tetrahedral, just like the electron domain geometry. If the molecule has 4 domains, one of which is a lone pair, the molecular geometry is called trigonal pyramidal. It is trigonal because of the 3 atoms at the base, and pyramidal because the central atom forms the tip of the pyramid. If the molecule has 4 domains, 2 of which are lone pairs, the molecular geometry is bent. Again, it looks like you took a crowbar and bent it. An example with this molecular geometry is water. Even though we draw the Lewis structure of water very boxy, it's actually got this very angular shape. You'll notice in the drawings that there are straight lines, wedges, and dashes. Straight lines are in the plane of the screen or paper. Dashed lines are pointing away from you. Wedges are pointing towards you. It is a way of representing 3D shapes on a 2D surface. Notice I draw the same configuration of wedges, dashes, and straight lines for all the molecular geometries within a category. I start with the basic tetrahedral geometry drawing and just replace atoms with lone pairs if necessary. When there are 5 domains, the molecule has trigonal bipyramidal electron domain geometry, corresponding 90, 120, and 180 degree bond angles, and sp3d hybridization. 5 domains with 0 lone pairs has trigonal bipyramidal molecular geometry. 5 domains, one of which is a lone pair, is seesaw molecular geometry. The seesaw is actually on its side, the way I've drawn it. The atoms pointing up and down would be where you would sit on the seesaw, and the atoms in the equatorial plane would be the struts holding up the seesaw. I've just drawn it this way for consistency's sake, so you can clearly see axial and equatorial. If you own a model kit or can afford to buy one, I encourage you to use it to build these molecules, especially for the seesaw molecular geometry. If you can't build with a modeling kit, the next best thing is to use the simulation on the PhET website linked on this slide. Please play around with it for all your molecular geometries and try to build as many molecules as you can. 5 domains, 2 of which are lone pairs, is T-shaped molecular geometry. Again, the T is on its side. The axial atoms form the horizontal bar of the T, and the equatorial atom forms the vertical bar of the T. 5 domains, 3 of which are lone pairs, is a linear molecular geometry. Although the electrons are pushing in 5 directions, the atoms themselves are pointing in a straight line. When there are 6 domains, the molecule has octahedral electron domain geometry, corresponding 90 and 180 degree bond angles, and sp3d2 hybridization. 6 domains with 0 lone pairs would be octahedral molecular geometry. 6 domains, one of which is a lone pair, would be square pyramidal molecular geometry. The 4 atoms in the plane form the base of the pyramid, and the top atom forms the tip of the pyramid. 6 domains, 2 of which are lone pairs, would be square planar molecular geometry. Notice the electrons are directly across from each other, and the atoms are all in a plane. 6 domains, 3 of which are lone pairs, is a T-shaped molecular geometry. Again, the T is drawn sideways for consistency with the other octahedral drawings. 6 domains, 4 of which are lone pairs, gives another linear molecular geometry. What is the molecular geometry of the SF4 molecule? Is it A, seesaw, B, square planar, C, tetrahedral, or D, trigonal pyramidal? The correct answer is A, seesaw. To answer this question, first you are going to need to draw the correct Lewis structure. The question won't always say, draw the Lewis structure, but you'll need to know to do it anyway. If you just stop at step 2 with the stick figure, you will count 4 domains and say that the molecule has tetrahedral molecular geometry. That would be wrong. You have to do all 5 steps. Step 4 is especially important in this molecule because it tells us that in addition to the single bond CH fluorine, the sulfur also ends up with a lone pair. Therefore, there are 5 domains on the sulfur. 5 domains, one of which is a lone pair, corresponds to seesaw molecular geometry.